Is this semester is finished at the Vanderbilt?
Yeah.
Oh, cool.
Yeah, so the last week was the finals week.
Gotcha.
I guess everyone's kind of getting ready for graduation or vacations and all these kinds of things.
Awesome.
All right, I guess we can go ahead and get started. So, hi everyone, welcome back to another Vanderbilt ML seminar. And today we're happy to have Dongkuan Xu. He's a PhD candidate at Penn State and an incoming assistant professor at North Carolina State University. He's published numerous top ML conference papers, has had extensive experience in industry through internships, and today we'll be giving a talk on resource efficient deep learning. So
sure.
Thanks, DK.
Sure. Thank you, Tyler. Yeah, so hello everyone. My name is DK. And so I feel very happy to have this chance to give this talk. And in general, my research includes the artificial intelligence and machine learning and natural language processing. So in this talk, I will feel very happy to introduce some of my very recent research efforts. So for example, the next title is the resource efficient deep learning to democratize the AI at scale. And I will first talk about some of the background and give you the big picture of my research. Then I will introduce two of my significant contributions. And after that, I will do a summary of my research. Then I will share with you some of the future plan about the research. And so we have observed that in the past decades, the people prefer using the larger and larger the AI models and the AI systems. So for example, in this figure, the X represents different years, a Y represents the number of parameters indicating the model size of the AI models. So we can clearly see that there is the very significant increasing from in the past decades. For example, like in about 2014, like the VAE and the GAN model, their model size is smaller than the 10 million. However, in most recent years, like the GPT-2, GPT-3, they are more than 1 billion, more than 100 million, even 1 billion. So people found that the large model or the large scale, the AI model, they are quite powerful, can achieve the good performance in different downstream task scenarios. However, they are difficult to use in practice due to the high memory, due to the high memory requirements to download the model. Besides the model size increasing, there's another one. It's called the computation increasing. So you can also see in this figure, the X represents different years, a Y represents the computation associated with that model. So it is measured by the flops. So there are two lines in the figure, the red one and the blue one. The red one is the increasing in terms of the computation for the AI models. And the blue one is interesting, is the Moore's law. It means that the computing support from the hardware aside. So we can clearly see that there is the increasing gap between the AI development and the real support from the hardware from the Moore's law. So let me give you an example. GPT-3. So GPT-3 is an autoregressive language model. So it can produce some of the human-like text very smoothly. So in this figure, you can see we just need to give the GPT-3 model an input prompt, like the recite the first law of the robotics. So naturally, the GPT-3 can generate some of the new paragraph never seen before. So besides this kind of text generalization ability, GPT-3 can also be applied to many other application scenarios, including the NLP and the CV and the speech, etc. So however, GPT-3 requires a lot of computation resources. So for example, it requires more than 300 gigabytes of memory to load the model. It requires more than 300 years for training this model if you use a single GPU, and it also requires more than 500 gigabytes of data for the optimization. So the conclusion that we can get is that the AI at scale, I mean, like the GPT-3 model, and there are many other large scale, the AI models, they are powerful, but they are also resource hungry. As a result, there could be many resource, the challenges or the resource discrepancies, which has hindered the democratization of the AI techniques. So for example, in this figure, you can see, for example, like the large scale cluster, the tech giants, the developed areas. So they have enough money, they have many devices to experiment with the large scale AI. However, for the edge device scenarios, for the most of us, the individual researchers, and for most of developing areas, so people in this area or the scenario in this area, so the large scale AI or the most recent developments of the AI cannot be utilized very well. So my research is motivated by this kind of the real world, the resource constraints. So my research tries to address the three, the real world, the resource constraints. For example, like the memory limitation, and so which can be found like on your smartphones, on your personal devices, on some cameras, and also I want to address the issue from the sensitive data, which could make the data amounts could be very small. So because like some of the face images, it's very sensitive. So you cannot have many the face images to train your model. And also there could become the types of data could be sensitive. For example, like the medical records. In the medical records, some of the gender information could be very sensitive. And you cannot use this kind of sensitive information. The other one is the low power the constraint, as in the most university labs. So my research aims to address these issues from three aspects. The first one, I study the parameter efficiency, try to address the memory limitation and constraint. For example, I study the model compression. So the model compression aims to reduce the model size to make the model can be fitted into some of the personal devices or some of the memory constraint devices, and while at the same time, we hope to achieve a similar performance as the original, the big dense model. The second part, I study the data efficiency. For example, the typical problem is the feature learning task. So only given a few months of data, how can you train a model? How can you make the model to behave like the model which has the access to the whole data set? The last one, I study the computation efficiency. So for example, I study how to reduce the training cost for the larger scale the AI models, how to reduce the epochs, the number of epochs, how to speed up the convergency of the large scale AI model training. So overall, so my research aims towards the inclusive and the progress preserving and the green AI. So let me give you more examples. So the applications of my research. So my research is centered around the efficiency. So what is efficiency? So efficiency can be defined in my research. We want to use the less memory. I mean, in terms of the model size, the parameters, the number parameter, we want to use less data and less computation. At the same time, we want to achieve a similar performance as the original one. There could be multiple applications. The first one in the smart cities, and also the self-driving cars, the embedding systems. And also my research can be applied to the VR, AR, the healthcare, and AI for sciences. More specifically, my research on the parameter efficiency can be used to reduce the infrastructure costs and in the smart cities. So this is because like my research on the model compression. So model compression can reduce the memory requirements for devices. So in this way, the governments and the universities, so they can use the same amount of budget to buy more devices. And also, my research on this part, that model compression can also benefit the social inclusion. What does it mean? Social inclusion means that, so it can, because my research on the parameter efficiency can reduce the memory requirements. So in this way, we can enable the AI model, or the large scale AI model can be applied to more the smartphones with the different memory, with the different CPU or GPUs. So people have maybe they have the very smart advanced iPhone, but someone don't have, but they can still utilize the AI techniques by applying my research. The second part is my research on the computation efficiency can benefit the self-driving cars, because there are two key components for the self-driving car. One is how to make the real-time response. The second one is how to reduce the energy consumption, because you want the car, and sometimes like the electric car, you want it to run as much as faster, run as long as possible. So the last part is my research on data efficiency, and it can be utilized to model some of the very complex, some of the structural relationship especially in the AI sciences, in the AI domain, in the science domain, because in the biochemistry, in the bio or in the chemistry, the data instance, usually they have a much complex relationship than some of the typical ones, than the images. For example, some of the chemistry, the atom, they will they don't only have some of the spatial relationship, they also have some of the temporal relationship. So my research on like the graph structured learning can be utilized to apply in this area. And also my research on the functional learning can be benefits the privacy preserving learning. And also my research on the contrastive learning can be used to avoid the label information when we do the modeling. So this is the big picture of my research. So any questions now? Awesome. So let me continue. In the next section, I will talk about my first contribution on the parameter efficiency, a network pruning under the pretrain-then-finetune paradigm. The problem study in this section is that I want to study the network pruning under the pretrain-then-finetune paradigm. The goal is we want to reduce the model size of the large-scale pre-trained AI models to fit in the memory limited deployment scenarios. So first question, what is network pruning? So network pruning, and so intuitively you can understand it as the removing the connections between different layers. So in this figure, the left one is the original dense model. You can see there are 3 layers, and between between 2 layers, there are some connections. And on the right part is the model after pruning. So you can see some connections are removed. So these connections is also the width matrix and in the deep models. So in this way, by utilizing removing the connections, we actually reduce the number of parameters for the model. The next question is that what is the pretrain-then-finetune paradigm? The pretrain-then-finetune paradigm is the most popular and basic training pipeline or training strategy for the large scale the AI models. So we can see in this figure from the left to right, the large scale model will first be initialized randomly, and this model will be first fed into the pre-training stage. And the pre-train stage, after the output of the pre-train stage is the pre-train model, and the pre-train model will be then fine-tuned, will be fed into the fine-tune stage. And finally, we can get the fine-tune model on some task-specific datasets. So what is the difference between the pre-training and fine-tuning? The pre-training typically say that we will, during the pre-training stage, we will train the model on some large-scale datasets and in a very general way. For example, we don't want to use the label information, we just use the data itself. However, during the fine-tune stage, the pre-train model will do some more the task-specific training. So during the fine-tuning stage, the model will be trained on the task-specific datasets, but it only requires a few of epochs. So it's called a fine-tuning. So instead of the full tuning. So finally, my research goal is to reduce the model size, but without the compromising accuracy during the testing stage. So my research in this direction mainly focus on some of the large scale the AI model, especially for example here I studied the experiments on the based on the BERT model. The BERT model is language model. It proposed by Google in 2019. It is much complex than the previous language model. So we can see in this figure, describe the general architecture of the BERT model. So we can see the BERT model actually is the many transformer layers. They are stuck together. From the bottom to up, we can see the input is the x1, x2, x3. What's them? So they are the token. So x1 is token, x2 is the token, x3 is also token. So x1, x2, x3 is a sentence. So this sentence will be processed by each layer, the transformer layers, one by one, one by one, one by one. And finally, we can get the output. The output, what's the output? The output is the hidden representation or the hidden representations for each token. So, and also it contains the hidden representation for the whole sentence. So after we get the hidden representation for each token and or for the whole sentence, we can do many things. We can do classification. We can do prediction. There are many other downstream tasks we can we can utilize the hidden representation into the downstream task. And typical saying, each layer is the same, has the same architecture. So we can see on the left part, I shall more the fine-grained the model architecture of each layer. It mainly contains two important modules. One is the self-attention module. The second one is the two layers and MLP layers, the two neural network layers. You can see the W, the many W. Each W is a weight matrix. It's just linear weight matrix. So the main goal of the self-attention module is used to extract or modeling the relationship between different tokens. So it means that by the self-attention module can tell us x1 is more similar to x2 or is more similar to x3. So it can tell us the relationship between different tokens. The two layers actually is the instructor. It is used to instruct the hidden representation for each token. So that's their goals. There are some of the existing efforts in this direction. So one category, they try to apply the pruning during the pre-training stage. The second category is that the people trying to apply the pruning during the fine-tune stage. However, there are some limitations. The first one, that's the prune model, typically saying that the representation capacity is quite limited. For example, this figure shows the pruning results for the typical pruning methods. So we can see the left one is the original dense model, right one is the prune model. So we can see there are some layers are discarded. However, people believe that model with a wider and a deeper architecture, this kind of model usually they have a higher capacity. So higher capacity is positively related to the final performance of this model. But if you lose some layers, so the performance will be hurt. And the second limitation is that during the pruning, there could be part of knowledge will be lost. So we can see this figure. This figure describes the fine-tune stage. So the pre-trained model will be fine-tuned into the task-specific fine-tune model, and we will at the same time apply the pruning strategy during the stage. So because the pre-trained model it is trained on some large scale the data corpus, so it will contain some very general purpose knowledge. However, after the pruning, there will be only a small part of the knowledge will be kept. This because during the pruning, a part of the model architecture will be removed. So my research is also aims to reduce the knowledge lost during the pruning process. My first contribution can be summarized as the hypothesis. That is, network pruning will increase the risk of overfitting under the pretrain then fine-tune paradigm. So what's the meaning of this hypothesis? So this is the counter-traditional hypothesis. So traditionally, people in the community of the model compression or in the network pruning, people believe that the pruning will decrease the overfitting issue. This is because the prune model, it has less parameters. So people say that less parameters will have the less probability to encounter the overfitting issue. However, we found that under the pretrain-then-finetune paradigm, the prune model will have a higher the probability to encounter the overfitting instead of the lower one. So let me use one slide to show you. So this is also the overfitting issue. Actually, that is the reason why there is a lot of the knowledge will be lost during the pruning process. So our goal is to mitigate the overfitting issue, to address the overfitting issue. So let me use one slide to show why overfitting will happen during the pruning process. So this is mainly because there would be the extra knowledge will be lost during the pruning process. So you can see this figure. There are two circles, the inner one and the outer one. The outer circle represents the area for the general purpose knowledge. It's larger. And the inner circle represents the task-specific knowledge. It's smaller. So because when we do the pruning, so actually we will lose two parts of knowledge. One is the red one from the general purpose knowledge, and the other one is the black one. It's from the task-specific knowledge. So why overfitting will happen? So it is because we lose the red one. So because the red one so we lose the red one, the general purpose knowledge. So during the algorithms updating, the algorithm or the model will try to recover the red one automatically. However, in order to recover this kind of the lost knowledge, we need more data. But when we do the fine tuning, the data is fixed. We don't have more data. So this will lead to the data deficiency. And the data deficiency, it is the data deficiency that leads to the overfitting. So it means that the data is quite not enough for the large scale model. The parameter is still the same size, the same scale, but the data is become relatively less. So this leads to the overfitting issue. And the overfitting issue, it leads to the large loss during the process. So in order to address these limitations, I try to, for example, I try to propose the sparse pooling and to enhance the model capacity. And I also propose a series strategies to address the overfitting issue. For example, I propose the knowledge distillation as a regularization way to mitigate the overfitting issue. I propose the progressive learning to slow down the optimization for the large scale AI model fine tuning. So this progressive learning means that instead of updating the whole parameters, we only update parts of the parameters. So this is the progressive one. So we will first update the first layer, and a second epoch, we will update the second layer. Next one, we will update the third layer. So one by one. It's called the progressive learning. And that's one I studied, the generative learning, and so which can be used to augment the downstream task data. So that means that data we could generate more, and this can also benefit to address the overfitting issue. So in this talk, I will mainly focus on the first one, sparse pooling plus the knowledge distillation, the KD. First one, what is sparse pooling? Sparse pooling means that we want to remove the collections within layers while at the same time maintaining the model architecture. So this figure, the left one is original dense model, the right one is the proof model after the sparse pooling. We can see both of them have the same number of layers, but the difference is that within each layer of the proof model, there could be the zero values for in the weight matrix. So it means that the weight matrix is sparse, but we keep the architecture. So the right part is the typical structure pooling. So this is the comparison. Okay, so why do we want to do the sparse pooling? The first one, that the sparse model or the sparsity always show higher capacity for the deep learning models. So for example, in this figure, the X represents the computation and the computation associated the computation like the floating point operations. So it indicating the computation for this model, and the y-axis represents the performance in terms of the accuracy. There are two lines, the red line and the gray one. The red line is the sparse version of the efficient nets, and the gray line is the original dense efficient nets. So we can see under the same X value, the red line is always higher than the gray line. It means that under the same budgets of the computation, the sparse version of the model can always achieve higher performance. So this is the first the benefits. The second one is that the sparsity or the sparse design of the is quite popular. No, it's not quite. It's quite general. So we can find the sparse kind of structure can be almost in every deep learning models. So for example, according to the ICLR 2009, the ICLR 2019 best paper, the lottery ticket hypothesis, we can find that. So this best paper indicate that for every dense deep learning models, we can find inside that model there is the sparse subnet works which can achieve a similar performance as the original dense model. So it means that for every deep learning models, we can find inside that model a smaller one, which a smaller and sparse one, which can achieve the similar performance as the original dense one. So it means that we can apply the sparse strategy into almost every deep learning models. There could be other support from the other communities. For example, like people in the hardware or system. So people also believe that the sparsity or the sparse model is the key component for the AI tool. So my method is the sparse pruning plus the knowledge distillation. So what is knowledge distillation? Knowledge distillation is the learning framework for the teacher model and the student model. So you can see in this figure, this is the illustration of how the knowledge distillation works in general. So the teacher model usually is a larger one, and it is already pre-trained on some of the data sets. And the student model is generally a smaller one, and it is our target. We want to generate a student model which is smaller than the teacher model, but we hope the student model can have a similar performance as the teacher model. So given the input data, then the input data will be fed into the teacher model and the student model. And what we do, so we will try to minimize the outputs of the teacher model and the student model. So in this way, we will force the student model to have the similar behavior as the teacher model. So I want to say that knowledge distillation is also quite a good way, a very practical way to improve your performance. If you study like the transfer learning, if you study the multitask learning, if you study some of the domain adaptation, so everything, if your research is related to the transferring, you can consider the distillation as a very practical way to improve the performance. Okay, so let me use one slide to show what's my proposed methods looks like. So this is the student model. This is our output. So we can see there are multiple layers, and there's also at the bottom there could be some input the tokens. And for each layer, we can see there's some weight matrix. But the difference is that we will apply the pruning to this weight matrix, every linear transformation matrix. So, however, if we intuitively applying the pruning to this weight matrix, the performance will drop because you lose a lot of parameters. So in order to recover this performance, I utilize another model as a teacher model. This teacher model is already pre-trained on some very general task. So when we prune the model, we will try to at the same time distilling the knowledge from the teacher model into the student model. So you can see we will So you can see there, this is the only demonstration between the keys layer. We will apply this strategy for each corresponding layer. So this is called the layer-wise knowledge distillation, the layer-wise KD. Now let me give you let's see some of the experiment results. And we conduct the experiments on the group benchmark datasets. And the group benchmark datasets is a popular and the datasets task for the natural language processing. And this column indicating the weights after pruning. So for example, at the bottom, this is our method. So 5% means that after the pruning, we only keep 5%. So we will remove 95% of parameter. There's these 4 columns indicates the tasks from the group benchmark datasets. And the right one is the average performance. It's just average performance for the left 4. So the bottom one is our method, sparse. So there are some baselines. So compared to this baseline, our methods can achieve a little higher performance, but more importantly, that we can remove much more parameters than these baselines. Even compared to the original dense model, I mean, we can remove 95% of parameter, but we only have 1.4 performance drop. Besides the study on the reduction of the parameters, we also study the reduction in terms of flops. Flops means the floating point operation. So indicating it indicates the computation and the budget for that model. So compared to the original dense model, our model can achieve like about the 20 times the reduction in terms of the flops. Okay, 3 takeaways. So I propose the sparsity to enhance the model capacity. So if you are also studying the deep learning methods, so if you found that your method does not show good performance, you can design a model into the structure, the sparse structure, in order to enhance the capacity. I also studied the knowledge distillation to transfer knowledge from the teacher model to the student model, from the very big one, this one, or the sparse, the smaller one. So if you are studying the transfer learning problem, if you are studying the multitasking problem, if you are studying the domain shift or domain adaptation problem, you can use the knowledge distillation as a way which can show very practically good performance. And lastly, I proposed the counter-traditional hypothesis and the 3 specific methods to compress the large-scale pre-train the AI models. So if you also study the large-scale AI model like the BERT or the GPT-3 or Roberta or T5, you can, if you cannot download the model into your personal devices, you can first apply my methods, and after that you can play with these models further afterwards. So this is my contribution, my first contribution. And any question now? Awesome. So let me continue my talk. So in the next section, I will talk about the computation efficiency. So I studied the neural architecture search to distill the compressed model. The motivation for this section is that, so in the second section, we say that we can generate a very efficient smaller model. But typically, in order to generate such kind of efficient smaller model, you need to pay a lot of training cost. You need to pay a higher cost, like the training time, a lot of the money. So in this section, I try to reduce the cost for generating these efficient smaller models. The motivation is that in the real world, we can find that the resources constraint limitation is quite various. For example, like the cloud AI, mobile AI, tiny AI, they will have different memory requirements or different computation budget requirement and constraints. So if your method is task specific one, you will apply your methods to each scenario one by one. So this is very time consuming. We want to avoid that one. The second one, that even if you only train or you only do the compression for once, you will still have the energy issue and or environment issue. So in this figure, it shows the the carbon footprint benchmarks. So we can see there's multiple rows. The first row is the carbon dioxide the emission for the round trip flight between the New York and the San Francisco. The more interesting is the bottom one. So this is the carbon dioxide emission for training a single transformer model. So you can see the conclusion is that, so even train a very single, the large scale, the pre-trained AI model, the carbon dioxide emission could be 5 times in the lifetime emission of the average US car. So this is unacceptable. It will do very bad things to the environment. So my research in this direction wants to make the training, make the compression more efficient. And also, I want to make the training to be more faster, to reduce the energy consumption, and also to benefit the environment. My contribution in this direction can be summarized as a framework. So I propose a few shot neural architecture search methods to distill the multiple compressed models all at once. What does it mean? I mean that my goal is to that instead of generate the compressed model, one for each scenario, the other one for another one. So I try to generate all the compressed model at once. So this can avoid the repeated training to get the compressed model. So how can we achieve this goal? So let me give you a very general illustration of my framework. So we want to train a huge model. This is a huge AI model, and we only train this model at once. And so the right one, they are indicating some the downstream tasks, the requirements in terms of the model size. So for example, so when we have the different requirements for the different scenario, we just need to search from the AI models to search from the very huge AI model to extract some parts of it to meet the requirements for a downstream task. We don't need to apply the compression from the scratch. We just need to search from the already trained model to meet the requirements for a downstream task. So this can avoid the repeated training, repeated of the compression process. So in order to achieve these goals, I propose the two methods, and one is called the task-agnostic super language model. I call that the super LM learning. And the other one, I propose the efficient lightweight vision transformer. The first one is target the natural language processing domain. The second one is target at the computer vision domain. But they share some the same techniques. One that I design the task-agnostic loss. The task-agnostic loss means that when we train a model, we don't use any neighbor information. So in this way, when we have multiple different downstream tasks, we can only use the same model to apply to the different tasks. I propose a super network training. So we only train a single huge AI model and not the smaller model one by one. And then lastly, I designed the search strategy to return the optimal candidates for the downstream task. So in this talk, I just very briefly go through the first one, the super language model. So because my research is focused on the transformer, like focused on the birds, focused on the pre-trained AI model. So we first need to identify what's the most important parameter for what's the most important architecture for the transformer architecture. So we identify 4 important ones. The first one is the number of layers. The second one is the hidden dimension, and also some of the other ones. So for example, like the number of layers, it had a big influence on the model capacity and the model performance, because usually the deeper model, you have a higher performance. And also the hidden dimension indicates the width of the model. So usually wider is better. But given a constraint, how can you get the good performance? And that's the problem we are targeted at. So the other strategy we used is that we divide the original, the transformer architecture search space into 3 subspaces. So for example, the original search space, so it has it allows the 12 layers, but we divide the 3 subspaces and make the 3 spaces can cover different range of the layers. So for example, we design 3 ones, the super LM tiny, super LM small, and for each of them, they will cover different number of the flops and number of parameter. So when the user give us the requirements, so say, oh, we want the model to be smaller than 10 million. So we just need to do the training to the training and the search from the first super language model, the super LM tiny. I'll say the user we want the model to be smaller than 8 million. So we just want the model to be smaller than 8 million, but we want to use power as much as possible. So under this scenario, we will target at the super LM base, the most right one. So this is the design strategy. The benefits of this design that after dividing into smaller subspaces, we can avoid some of the optimization conflict between the different subnet works with the different size. So I just ignore the details. I don't go through the details here, but there could be very detailed information you can find in my paper. So I say our method is that we are given a huge model. We want to extract a subset work from the huge model. So how can we do the extraction? So this is the right one is the super language model. So this is the one we train. We only train this model. And sorry. And the next one that we will do the first one, in order to get the subnet works, we will first extract the L layers from the super language model. So you can see this L layers. And after that, we will extract some of the sub-metrics from each weight matrix. So because we already described that for each layer, there could be many weight metrics indicated by W. And for each W, we just need to extract a part of the weight matrix because we don't use all of them. In order to reduce the number of size, we reduce the number of parameter. And last one, we also extract a part of the attention heads. So here, the heads, so the pretrain, like the transformer model, it will has different attention heads. It has the 12 attention heads. And each attention head is an independent computation process. So people already found that there is a lot of redundancy among the attention heads. So for many tasks, we don't use all the 12 attention heads. We just need part of them. So that's why we want to extract H heads. So this slide describes the training. I just very briefly go through the training, the pipeline. So we will first sample multiple subnet works from the super language model. So previous slide, we described how to extract a subnet work from the super language model. So we will sample the subnet works multiple times. And for the second step, that for each sample subnet work, we will do the distillation between the sample one and the super language model. So there could be multiple pairs. The third step is that for each pair, we will get a loss. So after we get all the losses, we will accumulate them together. And after getting the accumulated loss, we will use the loss to BP to update the super language model. So the most important thing here is that we design the task-agnostic distillation. What does it mean? So it means that when we do distillation, we don't use the label information. We just use what do we use? We just use the information from the attention components. You can see the QKV is the query, key, and value. So it's from the attention module. So we only try to minimize the pattern in the QKV from the teacher, the right one, and the QKV pattern from the subnet works, left one. We try to minimize the difference between the QKV. So in order to make the subnet works to have a similar performance at the right teacher one. So that's the general idea. We only focus on attention module because people found that attention module contains the most of the information for the transformer layer. for the transformer architectures. I also designed some of the search strategies, and so I don't go to the details here. The main goal is that so when we know the user, we can have a lot of the candidates which can meet the requirements from the user, but we will return the optimal one for all the candidates. So that's the search strategy. So we can see some experiment results. In this figure, X represents the flops, Y represents the accuracy. So the red one is R1 and the blue one is the baseline. So our method can achieve a similar performance as the blue one, but you can see in terms of the X value, our methods requires much less flops. There could be another comparison. So we can have a higher performance with the same number of flops. This is another comparison between the accuracy and the parameter. We can see our method always achieve a higher or a better the trade-off between the accuracy and the number parameter. 3 takeaways. The first one, I propose the super network learning, which avoids the repetitive model compression process. I designed the task-agnostic training and the search strategy which can be applied to many different scenarios. And also I developed the architecture search framework and the tools methods to automatically distill the compressed model for the NLP domain and also the CV domain. So any questions for my second contributions? Thank you. So let's go to the next one. So I will do very efficiently, very briefly. My research is focused on the resource efficient deep learning. So it's motivated by the real world resource constraints like the memory, like data, and the computation power. My first one is study the parameter efficiency, like the sparse model compression. I also study the modular networks. And modular networks mean that each node in the modular networks is the subnet network instead of the neural. So the benefits of the modular networks is that it's more robust. It's of a higher, better generalization ability. I also study how to improve the data efficiency. I study the feature learning, the contrastive learning. Contrastive learning is the unsupervised learning methods, learning problem. And I also study the heterogeneous learning, especially in the graph domain. I also study how to improve the computation efficiency. For example, we have several submissions this year for the ICML 2022. And we also have some the patterns for the improving the computation efficiency. And there is some other my collaborated work and for the NLP, in the graph, in the GNN, in the reinforced learning, the urban computing. And for the future, I think I have the short-term and long-term. The short-term, I will mainly focus on multimodal data efficiency because I'm very interested in a single learning system which can handle data from your vision or also your speech and the text. And I will also study robust and adaptive parameter efficiency. So for example, we know right now there are many new tasks generated by human beings every day and many new data sets. So how can we efficiently transfer the existing large-scale AI methods to a new scenario, which is very interesting and very economical. So in the long term, I would say that my vision is that the long term, the AI would be the algorithm hardware co-efficiency. For example, we will study like the database integration, the privacy, and system security. So in order to address this challenge, I will study the tiny machine learning and parallel computing design and real-time system. And so this is the future plan. And this is some collaborators and the support from different agencies. And thank you so much for your listening. And I'm very happy to answer any questions from you. Thank you.
Thanks, TK.
Thank you so much. Thank you. Yeah. So I can answer any questions.
Yeah. Thank you, Dongkuan. Great presentation. I have a question regarding your layer knowledge distillation.
Yes.
In the first part of your project. So do you do the knowledge distillation like requiring your prune network to output a similar representation to your original network?
Oh, yes. So your question is that how do we do the distillation? So what's the object function for distillation? Is that right?
Yeah, kind of.
Yes. So typically, when we do a distillation, we try to and make the outputs of the teacher and students, they have the similar outputs, but you can have the different, it's quite flexible. You can make the logics to be similar. You can also make the hidden representation to be similar. So you can also make some attention, the pattern to be similar. This is quite possible. It's quite flexible. But typical one would be the logics and also the outputs label, the hard label, the prediction.
Yeah, got it. So follow-up question is like, so if like say when we apply the prune network on unseen data that have not been used for that knowledge distillation, how can we ensure that like based on our training data on that knowledge distillation, we can have some inductibility that even for those data that are not in the knowledge distillation, still our prune network can apply to that?
Awesome. So this is a great question. So your question is that if we encounter the domain shift or distribution shift, how can you do a good distillation? So you mean that when the model, the train is on A domain or the A distribution, but we testing the model into the B domain or the distribution. How can we do that? So this is very interesting. This is also very practical in the real world. A typical way we can do that. So when we do distillation, we can choose a teacher model which has already been fine-tuned on the downstream task. So you can have the teacher model. This is the pre-trained, and you can also fine-tune the model on the downstream task. So when you do distillation, you want to distill knowledge from the fine-tuned model into a smaller model. But the teacher model is already been fine-tuned. So you can distill both the general purpose knowledge and the downstream task knowledge into a smaller model. Yes.
Gotcha. Yeah, that makes sense. Thank you.
Yeah, yeah, no problem. I want to say another ways. So the other way is that you can do augmentation. So data augmentation is quite popular in the CV domain. So because in the domain is shift, so you want to increase the domain adaptation for the downstream task. You can do data augmentation for a downstream task. That's quite also very practical. Yeah.
Okay.
Yeah. Yes.
Gotcha.
Thank you for your question. Yeah.
Thanks.
So, I mean, following on that, I have a question about the sparse pruning, right? So sparse pruning is like it has been studied a lot, right? But like recently, there are some papers that show the role of training in the effectiveness of the sparse training. I am not sure if you have seen the power propagation paper, right? Essentially, train a network such that the parameters are more prunable, I should say, like, or it's going to be fine if you prune the network. Have you looked into like different training regimes for your sparse pruning?
Oh, so you mean so your question is that what happened during the pruning process? So
no. So the dense model is trained with some optimization, some optimizer, right? So I'm asking, like, have you looked into like the type of optimization that's used to train that dense model? So for example, if you use power propagation, that dense model is going to be more suitable for pruning. So you will be able to prune more of that network. But given that you're an expert in this, I was wondering if you have looked into the different optimization scenarios for the dense model, and what is the effect of that on your pruning?
Awesome, thank you, Sohail. So I think I haven't studied in this area. So because my research focused on I designed some general purpose for the pruning. So typically the pipeline is quite popular one. So I choose the most popular, the typical one in the CV or NLP domain. But you mentioned optimization. Yes, there are studies like you mentioned about the power propagation. So there could be some of the difference, but there could be a different influence on the pruning results. But I haven't studied that one. That's very interesting. That's very recent. I think that paper is this year or
2021.
Yeah,
2021. Yep.
Yes. Thank you for a question.
Yep.
So I guess a follow-up on this pruning direction. I think that you mentioned something like 5% of the weights remaining in your model as compared to some of these others at like 50%.
Yep.
That what is the relationship between the percent removed and the performance? Because it looked like the performance was still very close. And I was wondering that, you know, what if you push it to 1% or if it's at 10%?
Yes, so this is very interesting. So generally speaking, when we remove more parameter, the performance will be, there will be a performance drop. So for example, if you consider the X as the number of parameter to be removed, so at the larger X will indicate the more parameter to be removed and the performance will decrease. But typically saying, they're very interesting. So typically say for the deep learning model, if the number of parameter is pruned between the 0% and the 50%, typically in this range, the performance will not have a good, there will be no biggest performance drop. So this is because the deep learning model usually are redundant. So you are removing some noise for the training process. So at a lower the pruning ratio, the performance will not be affected a lot. But when we beyond higher than the 50% or even the 70%, the 80%, so even with 1% higher, the performance will have a big difference. So how to achieve a higher the compression ratio is very interesting, challenging. But people right now, we are transferring into another direction. We don't care about the absolute value performance. We care about the under the same budget. How can we achieve a better performance? So both of them have the budget of that 80% the 80% of the parameter to be removed. Which one can have better performance? That could be more the economical way or more the reasonable way for us to, yeah.
Okay.
I think yes. I think so. I think so because I also studied some the GNN or the graph modeling area, how to improve the efficiency. So previously I tried to reduce the model parameter of the GNN model to increase the efficiency of the graph modeling, but I failed. So this is because I found that for the GNN model, the bottleneck is not the model size. The bottleneck could be the data. The bottleneck is data itself. The data could be very large and data could be very noisy. So if we only focus on focus on model itself for the GNN area, so it does not return good performance, good results for us. So I'm very interested in the co-design or co-efficiency between the model and the data model co-efficiency for the GNN the direction. This is very interesting. So I think that's also a unique challenge for the graph domain because this is quite different. So yeah.
Yeah, I kind of read a similar paper like graph lottery tickets. So they focus on how to pruning the graph edges. Like yeah, just as you said, typically the model for the graphs are not very deep. They don't have so many parameters, but the graph itself may have many works we can do to improve the efficiency.
Yeah. So from 2020, I think Google there studies a serious work focus on how to do the data distillation and to improve the efficiency of the graph modeling. So they focus on how to distill the data, how to make the data better, how to extract the relationship better to improve the efficiency. So as a result, they don't use a very large scale data to get a good performance. They only use the very small graph. They can also do a good performance. Yes. So I believe that's in the graph or in the machine learning domain, the data and the model, the co-efficiency would be a solution to improve the efficiency. Yeah.
Makes sense.
I have a philosophical question, maybe like a high-level question, right? So, given that the interest is on reducing the like computation, the carbon footprint, right? Like we would like to essentially reduce our computation such that training these networks is not going to affect our environment, right?
Yeah.
But it seems like a lot of the work in the community is focused on like post-processing. Like we do the training, we do the distillation of like very densely trained networks on something that's smaller that can be deployed. That's great. But can we do something about like training these networks in a sustainable and efficient manner? Like, can we train in it for sparsely, ensure sparsity from the beginning?
Yeah, awesome.
Yeah.
So awesome. Thank you, Sohail. So this is the very popular topic right now. So I think you have a very good insight here. So this is called sparse training. So sparse training, so typically means that we train the model is already sparse. So this is because there could be some application scenarios. For example, in the smart cities, sometimes you need to update the model a few epochs. So, but you can't download the model into your camera at once. So you need to download the model, part of the into the memory and to the updating. So the sparse training means that we will keep the sparsity of the model. So we only update like the 50% of the model at each epoch. And how can we also achieve a similar performance compared to downloading the whole model? So this is the hot topic right now. So people can, so sometimes you can also consider another scenario is that the AR, VR domain. People use the wearable devices to achieve some of the functions. But sometimes you need to update your model. You need to update your personal devices to make it more related to your data. So in this way, you need to, but the devices is quite limited in terms of memory. So in this scenario, people also want to do the sparse training. So this is very interesting. So I also have some ICML submission this year. So the topic is how to speed up the convergency of the sparse training. Because one challenge in the sparse training that's because you don't update the whole parameters, how can you estimate the gradients more accurately? This could be challenging. So if you can estimate the gradient more accurate, so you can speed up the convergency. Yeah. Thank you. Yeah, this is the very hot topics, I think. Yeah.
Yeah, thank you. Thank you. Yeah,
No
I
problem.
agree.
So I guess another type of like philosophical question that I was thinking is that, so the one motivating example is that wanting to have one of these very large dense models, and you can kind of scale it down to, you gave the example of like different phones. Maybe someone has the newest phone versus developing areas that have not as powerful compute devices. And so although getting similar performances, is there any kind of concern of like quality of service or quality of prediction where someone that potentially maybe couldn't run these like large language models before because they had no GPU or a very small one, but by providing them the ability to run these smaller models, but if they have lower performance, I guess I'm just thinking of like societal impacts of enabling certain communities, but now if they have like deterministic output that's different than a higher quality device and kind of lower performance.
Yeah, so I think yes. So Tyler, you mean that there could be some study about how to improve the performance for some the devices with the lower the quality or lower the memory.
Yeah, I guess so. If you have the larger model and you have like various devices that are scaling down, and if you're training all of them kind of at the same time as well, kind of searching for the best one, would it perhaps be of interest to ensure that their performance is equal, for example, as compared to if I'm running the newest iPhone versus one from a few series ago, that my prediction performance might drop, say, 5%, for example.
Yeah, I think there could be some difference. Yes, there could be some difference. So especially when you have the devices have different the computation power, or they have different memory, so they will have different the outputs. The outputs could be very critical. So for example, sometimes maybe your memory maybe have the like more than half the memory than the other one. but this could be sometimes very critical. For example, if your memory is smaller, it means that you have less of the data to access. So this could be there could be results in some of the BIOS problem. So because sometimes your data is less and your data could be biased. For example, if because you only have a small part of very smaller part of data, it could be like the only focus on some of the for example, like the female, you only have the data for the female, but your model or your model is pre-trained on some of the very general, like the female and male. So, but right now your downstream task right now you only have the female, so there could be bias. But if you have a larger model, you have iPhone which can load more data, that could be the bias could be mitigated to some degree, and also it's about the optimization. So if your power is more power, and it will benefit the optimization of the smaller model. So you mean that the model if you use the high quality the smartphone, the high quality the phone, you can have a better performance. But I'm interested in how can we guarantee that the people with the lower one still can have a good performance. So I say that the people with the higher one, I don't think they will care more about have many concern about the quality. I think that we should care more about the people with the lower the access to data or lower the quality of the devices. So this is also called I call that one is the social inclusion. Yeah.
Okay.
Yeah.
I've seen some recent works, I think, that discuss the relation of the model compression and fairness, and that it actually sometimes improves. But I guess then it's improvement relative to one model to the next as compared to across models. But thanks.
No problem.
Tyler, this topic of fairness is actually quite interesting, right? If you look at like the top conferences in machine learning, ICMLI, Clear, NeurIPS, and all these, right? The requirement is that you have a lot of GPU computation, that you can train like big networks easily, right? Like, I think like you can easily show that if you don't have access to n number of GPUs, you wouldn't be able to publish in any of these conferences. so it's not very inclusive, I would say. Right?
Yeah.
That makes sense.
Yes, the fairness. I think the fairness, the bias is also they are the very critical the topics in the current modern AI in most recent years. Yeah, quite important. Yes. So we also one of my the in progress the proposal. I mean, writing the proposal is being written. Say we study how to make sure the fairness can be guaranteed when we do the edge computing. So because as we said, so when we do the edge computing, the data could be biased, and also the model could be biased. How can we guarantee the unbiased training learning for the edge computing scenarios? That could also be very interesting.
Wow. Yeah, it sounds like you have a lot of soon to come works that sound really interesting.
Hopefully. All
right, then yeah, I guess thanks again for the talk, and we really appreciated it. So
my pleasure. Yeah.
Take care.
Thank you, everyone. Have a great day.
Thank you. Bye.
Thank you. Bye-bye. Bye-bye.